Hello everyone, let's continue with the solution to GATE 2023 Aerospace Engineering paper. Today we will be doing fluid mechanics and aerodynamics solutions which came in GATE 2023. So the very first question from aerodynamics came as question number 11, which says the direction in which a scalar field phi has the largest rate of change at any point with position vector r bar is the same as that of the vector. So if you have any scalar field, for example, if I consider a Cartesian system like this, and we have, let's say, several points representing the values of the scalar field function like phi1, phi2, phi3, phi4, phi5, phi6, phi7, phi8, phi9, phi10, phi11, and so on. Let's say we are at this particular position vector r bar. Okay, so from this point, if we sweep the change in value at this point to any point like this, if we take the differences between this, let's say we find the largest change in this particular direction. So if this is giving you the largest change in the value of phi, then this particular vector must be the gradient of the scalar field function phi. So it is a vector quantity which points always towards the maximum change. So the answer to the question number 11 should be grad phi. Okay, let's move on to the next question. So the next question is from fluid mechanics and aerodynamics is question number 14. A two-dimensional potential flow solution for flow past an aerofoil has a streamlined pattern as shown in the figure. Which of the following conditions is additionally required to satisfy the Kutta condition? So in such a question, if you have ever studied something called Kutta condition, so before we do this question, let me explain you what the Kutta condition states. So basically Kutta condition is basically used to be able to evaluate the exact magnitude of the circulation imparted on the surface of the aerofoil so that there will be a flow will be leaving the surface smoothly. So suppose there is a flow taking place over an aerofoil like this. Okay. So in such a scenario, the flow will curl like this at the trailing edge and leaves. So this is the case for if we impart the circulation gamma small. Okay. Now, if we impart the circulation large, what will happen is already we are having a free stream flow velocity which is coming from this direction. Okay, and here is your stagnation points. So the at leading edge you have stagnation point near leading edge as this, which is on the lower surface, and near trailing edge you have the stagnation point at the rear like this. So suppose we impart a large circulation, what it does is there is the flow velocity which is coming in this direction. If we impart circulation, so this circulation will add extra angular momentum. Okay, So that will increase the linear velocity on the surface of the aerofoil. If it is too large, the stagnation point will appear on the lower surface like this. In this case, again the flow would curl like this near the trailing edge and would leave like in this manner. Okay, so now by seeing this, if we impart the circulation moderate in between these two such that the flow leaves the trailing edge smoothly like this. So by doing so, by applying such a condition, we will avoid the swirling of the flow at the trailing edge. Okay, what it does is it will remove the infinite velocity existence near the sharp trailing edges here. Okay, so you don't have to worry about the trailing edge. Apart from that, if you take an angled trailing edge like this, the flow coming from the upper surface and flow coming from the lower surface, if you look at it, the two streamlines will be intersecting at the trailing edge. So having two velocities in two different directions at a point is physically impossible. So by applying Kutta condition, we avoid that also. Okay, so we get a simple understanding of what is Kutta condition. Okay, now let's put this whole story together into a small picture like this, and we'll do our other discussions why further other things are required. So you must know a lot of things to be able to understand this. So we are having this Kutta condition, I kept it here. Then apart from this, now the question is about clockwise or anti-clockwise. Okay, now see, if we consider, for example, an aircraft. Okay, let us consider an aircraft like this. If I consider an aircraft like this, okay, now this aircraft, if the direction of the circulation that is produced around this is in this manner. Okay, so you are having a free stream velocity v infinity. Let's say this is the free stream velocity v infinity, and by having circulation like this, at a point on the surface of the body, you will have on upper surface, flow will get accelerated. So if I take the cross section of this aerofoil here, if I take this cross section, okay, it is going to be some sort of airfoil, let's say. Okay, so we have some sort of aerofoil cross section at that particular point where we are having this circulation gamma. Now at any point on the upper surface, if I take a point 1 on upper surface and a point on the lower surface which is 2. So at point 1 we will have velocity v infinity plus some velocity due to circulation, velocity induced due to the strength of the vortex. Whereas on lower surface we will have the velocity as v infinity minus the velocity induced due to the circulation. So flow gets decelerated on lower surface and flow gets accelerated on the upper surface. So this discrepancy in velocity leads to the difference in pressure P lower minus P upper greater than 0, and the body starts to generate lift. So by understanding this much, people think that the clockwise direction is correct. Okay. So in this case, to accelerate the flow and bring this stagnation point to this particular point, we needed clockwise. But imagine if there is an aircraft coming from left to right like this. So in that case, what will happen? If I apply the circulation in the clockwise direction on this aircraft and look at the cross section, some of the cross section or one of the cross section of this particular aircraft, that is aircraft wing, which is my airfoil, it's going to be something like this, let's say. And if I impart the circulation in this direction, so what is free stream velocity? You have to stop the aircraft and pass the free stream in the opposite direction. That is what is your relative wind, and you are having circulation. So on upper surface, in this case, the aircraft will be producing the decrement in velocity. That will be V infinity minus velocity induced due to the strength of the vortex at point 1. And at point 2, the velocity induced at point 2 will be V infinity plus velocity induced due to the point 1. So the effect of, if you apply the clockwise direction in this, there will be Vu, V lower will become greater than V upper. That implies P lower will become less than P upper, meaning there will be a decrement in lift. That is lost in lift, which is absolutely wrong. So the correct way of applying the direction of the circulation is such that the sense of that circulation should be such that it should always be applied in the direction which will, or in the sense which will accelerate the flow on the upper surface and decelerate the flow on the lower surface, such that we always keep getting the required amount of lift to sustain the aircraft in airborne or in flight, we can say. Let's move on to the next question. So the answer to this, before moving it to the next one, we should mark we have to add circulation of strength gamma. So less than or greater than doesn't matter here. So to bring this from here till here, we require the clockwise direction. So do not get confused with clockwise is positive, anti-clockwise is negative, like that. Okay. That all depends on from where to where your aircraft is moving. Fine. Let's move on to the next question in Fluid Mechanics and Aerodynamics of GATE 2023. Question number 15, if you look, it says consider the Glacier solution for the incompressible laminar flow. So he's talking about incompressible laminar flat plate boundary layer first and the Glacier solution. Okay. Among the following options, select the correct relation for the development of momentum thickness with distance x from the leading edge along the length of the plate. So we all know that Glacier solution for laminar flow over a flat plate airfoil, over a flat plate air or aerofoil need not be required, or over a flat plate kept at zero angle of attack, is given by, here our interest is momentum thickness theta, is given by 0.664 x by root over Rex, where Rex is the local Reynolds number, given by under root of u naught x by nu. So we can write this as, leaving all the constants as this, x by root x will be x power 1 by 2. So theta is directly proportional to x power 1 by 2. So the answer to this should be B. Let's move on to the next question. That is question number 16. So if we combine in a two-dimensional potential flow, the doublet is a limit of superposition of. So if we combine a source and sink, we get the doublet. We all are well aware of this. So by method of superposition, we can find psi of the doublet as the combination of psi of the source plus psi of the sink. So if we superimpose the two psis, let me take it from one of my last year notes of GATE 2023. So let's take this. So our interest was the combination of source and sink by the method of superposition. So we have here doublet flow. So when we combine source and sink, we get a doublet flow which looks like this. So this is the superposition of source and sink flow. This is the streamline pattern for it. Okay. So the answer to this question should be B. Then let's move on to the next question. That is question number 18. Okay. So the figure shown in the options are schematic of aerofoil shapes. So obviously they are not to scale. So for a civil transport aircraft designed for a cruise Mach number 0.8, which among them is aerodynamically best suited as a wing section. So different aerofoils or shapes are used in different category, but if you look at the Mach number that they have given, it's not a low speed Mach number, it's a high speed Mach number. Above Mach number 0.6 we consider all as high speed flows. Okay, not supersonic, though they are going to be high speed, considered as high speed flows, high speed subsonic flows. So locally the flow might accelerate and would become supersonic, forming a supersonic bubble which would terminate into a shock like this, giving rise to the shock induced boundary layer separations of this sort. So anyways, here the best suited aerofoil, because the critical Mach number of a supercritical aerofoil is pretty large. Okay, so it thereafter the drag divergence Mach number comes, at which the drag increases dramatically, so which happens in these three aerofoils, whereas the option D, the aerofoil that is given, is having a flat surface. So and it has large nose radius and a large camber at the trailing edge. So it's a supercritical aerofoil which depicts beautifully the large cruise Mach numbers and the large value of critical and drag divergence Mach number. So in fact, for other cases also you can learn, or for other variety of aircrafts also, from the figure that I have for you guys. So which shape of the aerofoil, where it will be used, this particular thing will help you. So you have low speed aerofoil, then you have the airliners. Okay, this is our interest now. Then propeller blade, then supersonic interceptor, then blackbird, then turbofan blade, then turbine blade, then dragonfly wing, dolphin flipper fin, then sailboats. So our interest was in the civil aviation aircraft. So the answer to this question is D. Let's move on to the question number 34. So in this, they have airplane A and airplane B are cruising at altitudes of 2 km and 4 km respectively. The free stream density and static pressure are given at both the altitudes. The differential pressure reading from the pitot static tubes is 3 kPa. So the delta P that is given to you is 3 kilopascal for both the airplanes. So this is constant for both the airplanes. For airplanes A and B. So this is same. Assuming incompressible flow, the ratio of cruise speeds of airplane A to airplane B. So the cruise speed for an airplane which is measured by the pitot static tube is given by 2 delta P by rho. For an aircraft at altitude, I will be taking rho A, rho B separately. So this is VA for aircraft A and VB is under root of 2 delta P by rho B. Why I am writing delta P? Because it's same, so no need to worry about it. And we were asked to compute the ratio of VA by VB, which will be obviously from above two equations. It will be rho B by rho A, which you can write as under root of 0.82 by 0.82 by 1.01, which happens to be 0.905. So round off to 2 decimal places means answer should be 0.9, or you can write 0.91 also. So I would put here 0.9. Then let's move on to next question, that is question number 45. So this question is based on the atmospheric model, the international standard atmospheric model. So dt by dh is nothing but the lapse rate. So h is the altitude and dt by dh, that is the temperature gradient, is called as lapse rate. So they gave 4 different options. So let's look at first how the lapse rate is in the atmosphere. So for this, let me have from our previous class notes, let's take this figure. Okay. So this is how the temperature varies in the atmosphere with altitude. Okay. So if I draw in this some sort of lines like this, so this, it is already there, but I am drawing up till this. So there are certain regions which is our interest now. So up till 11 kilometers, here the lapse rate, that is the lapse rate, lambda is given by dt by dh. Okay, so here the dt by dh, that is lambda, in this particular region, the lapse rate, that is dt by dh, is negative, whereas in this region the lapse rate dt by dh is 0. There is temperature is constant along this line. Okay, whereas here it is negative, here it is positive. So if you know that much, you can directly answer this question. So whereas here the lapse rate dt by dh becomes greater than 0. So in the stratosphere there are two regions, one is called lower stratosphere, another is called upper stratosphere. So in the lower stratosphere the lapse rate is 0, or the temperature gradient you can say is 0, and in the upper stratosphere it is positive, it is greater than 0, whereas in the troposphere the lapse rate is negative. So the answer to this is 7 kilometers. So it is a region of troposphere. So it is the correct one. Negative 9 kilometers. Obviously wrong. 15 kilometer. That is above the tropopause. This is in the lower stratosphere region. So this is the correct answer. Then 35, which is above the lower stratosphere, in which the temperature gradient should be positive, which is true. So the answers to this question should be A, B, A, C and D. Let's move on to the next question. For an aerofoil, which of the relations given about the critical Mach number and drag divergence Mach number is slash R correct? So before you answer this question, you must know what is critical Mach number, what is the drag divergence Mach number, and what is the sonic Mach number. So let's consider an simple airfoil. Let us consider an airfoil like this. Now, if I take an airfoil like this and I supply the flow over this airfoil, let's say this is the free stream Mach number m infinity. Suppose the flow is getting accelerated and I achieved m equal to 1 for the first time. That time, this free stream Mach number is called as the critical Mach number. So, critical Mach number is a Mach number for which the sonic flow is judged on the surface of the aerofoil. So, it is nothing but the free stream Mach number. Okay. Then, if we further accelerate this flow, if I further accelerate this, one second, let me crop this. If I further accelerate this flow, instead of getting m equal to 1 here, I'll be getting m at a further ahead of this point. Very quickly the flow will, because I'm accelerating the flow. Now this, if this is m infinity 1, this will be m infinity 2. So I get m equal to 1 here. Thereafter I have further chance of further acceleration. So flow forms a sort of bubble here. This bubble is called as supersonic bubble. So this is a supersonic bubble. So if we have a supersonic bubble and we further increase, suppose I take this and I further accelerate the body, or I can say if I fast increase the free stream value. So what will happen to this flow? Now the Mach number will come here. So now this m infinity 3, so m infinity 2 is greater than m infinity 1, m infinity 3 is greater than m infinity 2, and the flow will accelerate, giving rise to the big formation of the supersonic bubble. Let's say this m infinity 3 is such a Mach number at which this supersonic bubble grows and terminates into a shock, kind of lambda shock. This is a shock, usually the lambda shock. Similar thing would be forming here as well. So this shock will induce, the flow will experience the shock induced boundary layer separation. So the flow will be separating like this. So this is called as, so this phenomena in aerodynamics is called as shock induced boundary layer separation. So when that happens, this Mach number, there will be a huge increment in drag. So this Mach number is called as drag divergence Mach number. If we draw a plot of this sort of the drag coefficient, if we draw a drag coefficient versus the free stream Mach number, it goes like this. Doesn't change. Then after a certain free stream Mach number increment, it's, so this is the point at which it started to rise. So this is rise. It is m critical. Okay, at which you will get the first sonic state. Then after a little increment, the drag will dramatically will start to rise like this. So the Mach number at which the drag rise starts to take is called as drag divergence Mach number, and the Mach number 1 would lie somewhere here. So it is clear from this figure that M critical is less than MDD is less than 1.0. Whereas for a flat plate kept at a zero angle of attack, all three would be equal. M critical will be equal to MDD, it will be equal to 1. Okay, kept at a zero angle of attack obviously, if it is a flat plate. Whereas for aerofoils, it should be M critical should be less than MDD should be less than 1. So obviously M critical should be less than 1 since MDD is less than 1. And M critical is obviously less than MDD. So the answer to this question is A, B, C. Now coming to the question number 56. A thin cambered aerofoil has lift coefficient CL equals to 0 at an angle of attack alpha equals to minus 1.1 degree. Assuming that stall occurs at much larger alpha, so we can consider the linear profile by reading this particular line. The CL at alpha equals to 4 degree is. So it's a kind of straightforward question. You can just find the slope of the dCl by d alpha or the aerofoil. Okay, so you can write simply the lift curve slope of the aerofoil. It's given as dCl by d alpha, which is equal to 2 pi for a thin aerofoil. So if it is 2 pi per radian it is. I will like to convert this into per degree. So for that I will multiply with, it's not radian to degree, it is per radian to per degree. So you have to multiply with pi by 180 to get it in per degree. Okay, which happens to be 0.1096 per degree. Okay, so you can equate this value dCl by d alpha can be written as Cl minus 0 by alpha minus alpha at L equals to 0, which is equal to Cl minus 0 by 4 degree minus of minus plus 1.1 degree, which is equal to 0.1096 per degree. So this is in per degree and this is in per degree. Now you can directly compute the non-dimensional coefficient as CL as 0.559. If we compute, you'll get. So rounding off to 2 decimal, we should mention 0.56. So the answer to this should be 0.56. Fine guys, moving on to the next question. In a potential flow, a uniform stream of strength U directed along the x-axis and 4 line sources of strength pi by 2, minus pi by 3, pi by 4 and minus pi by 5 are placed along the x-axis at x equals to 0. So there is a superposition of, we can say, a uniform flow with a, first you have the source, then you have a sink, then you have a source, then you have a sink. Okay, of different strengths. This strength is pi by 2, this strength is minus pi by 3, this strength is pi by 4, this strength is minus pi by 5. Now the question is, what should be kept here such that it all will encapsulate it into a circle like this? Okay, everything will get encapsulated. So by method of superposition, the strengths can be added like this. So pi by 2 minus pi by 3 plus pi by 4 minus pi by 5 plus the strength of the next line source should be net equal, must be equal to 0 to form a rigid body condition. So when you do that, you'll be getting m as minus 0.68, rounded off to 2 decimal places. Okay. Now, looking at the last question from the aerodynamics section, there's a term called entropy. So entropy is given by, or entropy is given by mod of curl of V bar whole square. It is also given that entropy is defined as the square of the magnitude of vorticity. So curl of V bar is nothing but the vorticity vector. Instead of zeta bar, you better write xi bar, which is curl of the velocity vector. So if we start hunting for the entropy, it should be mod of this. So first find the vorticity. This is the vorticity, which is given by I cap into dou w by dou y minus dou v by dou z, plus j cap into dou w by dou x minus dou u by dou z, plus k cap into dou v by dou x minus dou u by dou y. So I cap into, we'll be getting this as 0.7x, since your w is this, v is this, and u is this. So you have uvw as the components of the velocity in x, y, z direction respectively. So we'll be having this as I cap into 0.7x minus 0 plus j cap into 0.7y minus 2.5 plus k cap into 1.5 plus 1.5. So this happens to be 0.7 I cap plus 1.8 j cap plus 3 k cap. So if we find the magnitude of this vorticity, we'll be getting magnitude of the curl of the velocity vector. That happens to be root over 0.7 square plus 1.8 square plus 3 square. So our interest is entropy, which is square of this quantity. If you take the square root of this, it happens to be 12.73. So our answer for this blank is 12.73. Fine. Okay guys, those who find this lectures interesting, please follow my next video on gas dynamics and rocket propulsion. Thank you.